I'd like to talk to you now about magnetic properties of matter. Um, Unlike electric charge, magnetism is not fundamental. That there is a mantra that I like to use, which is that the source of all magnetism is moving charge. And when you think about motion, that has to call into question motion compared to what. In other words, relativity has to come into this because if I, for instance, am in a moving car that I am moving relative to the ground and other things that are exterior to the car, but relative to the car, unless I'm in an accident or in some other way moving within the car, that I have no relative motion within the car, which is to say, if I were to be driving along at a constant velocity, for example, that if I were to take a coin and toss it up in the air, to a person outside the car, they would see that coin moving with a relative horizontal velocity as well as flipping up and flipping back down. Whereas to me, it would just move up and move back down, slowing down on the way up and speeding up on the way down. And so motion is very much relative. And so when we talk about magnetism, it is in a relativistic effect because there has to be relative motion of a charge for that charge to create a magnetic field. So that might seem a little esoteric, but it can come into play in real world examples, but I won't delve into that at this point in time. So if I want to think about magnetism always being created by moving charge, then I can use several different examples of magnets and talk about what charge is moving to create that magnetic field. And so a simple one would be an electromagnet. And so you see an image here of a 9-volt battery. And by the way, I'm going to take a quick side trip here. That battery, by definition, means a collection of some things. And in the case of electrical, quote, batteries, that many of what are called batteries are not batteries, that they are actually cells, that a typical cell is able to, typically through electrical interactions, create a 1.5 volt potential difference between one terminal and another. And so if you have a 1.5 volt quote battery, like a D cell, a C cell, a AA, a AAA, or many of the little button quote batteries, that those aren't really batteries, because if they are 1.5 volts, they are truly cells. If you have a combination of cells, that is a battery. So some of the button cells are 3 volt, and so those are truly batteries because they have 2 cells in them. This is a 9-volt battery, so you know it must have 6 cells within it. In your car, it has a 12-volt battery, so you know that it must have 8 cells. 8 times 1.5 gives you 12. So that's my little rant about batteries, that if you're talking DC, AA, AAA, etc., those aren't batteries. Call them cells. So here we have a 9-volt battery, and then that wire looks like it's kind of bare copper, but it isn't. It couldn't be and have this work, because if that were the case, then those loops that are going around the nail that are touching each other would short is the electrical term oftentimes used for electricity taking a shortcut. It would short through all of those touchings going on, and plus it would also be touching the middle of the nail, and that would short it out. And so this is what's oftentimes called magnetic wire. It's not because the wire itself is magnetic, it's because it has wire that has been coated with an enamel or some type of insulating paint that oftentimes is clear, so it looks like you're looking at bare copper, but you're not. That copper has been coated. And so you see it's looped around the nail. Now, I would encourage you to do this at home. One warning is that wire will get pretty hot, because you know that when you run electricity through wires, the wires can get hot. All you have to do is look at your toaster or toaster oven, etc. Possibly your stove, if you have an electrical stove, and you'll see that you can get stuff hot by running current through different types of wire. But if you were to make this connection at home, and you can use a D cell, a C cell would pretty much run out of its useful electrical processes fairly quickly. A D cell would certainly last longer, and then this 9-volt battery wouldn't last as long as a D cell, but the electrical field that it would generate would be much higher. But if you hook this up, what you'd see is that little nail that's down beneath would probably jump up and attach itself to the large nail above, because it would be magnetically attracted. And you could also play around with switching which terminals, which side of the coil connected to, and you would see that it would still jump, that the little nail would still jump up and attach itself. It doesn't care, but by changing the direction that the electricity flows, and that's kind of redundant, I probably shouldn't use that kind of locution, but if I change the direction of the flow of electrons through this wire, then I'll change which end of the nail it's wrapped around is north and which is south. But another piece of metal nearby, if it's a magnetic material like that little nail that's lying on the table, it would be attracted to either or north or a south end. But if you had a compass handy, you would be able to detect the difference between what end of the nail was north and which end of the nail was south if you swapped the connections. So in this case, what is happening is that conductor copper in this wire has electrons that can be motivated to move through the potential difference provided by the 9-volt battery. And so it's those electrons moving that cause a magnetic field. Now, if you were to delve into physics, or if you have delved into physics previously, you'd probably run across something called the right-hand rule that has to do with charge motion and magnetic fields and forces, etc. One of the reasons I don't really jump into this in a major way is because all of this is based on positive charges. And so, for example, in this situation, if I had a positive charge that was moving to the right here, like this arrow indicates a velocity, that it would experience a magnetic force up if the magnetic field, which is B is used for magnetism, which I don't know why B was chosen, but anyways, then there would be an upward force if the magnetic field was into the screen, or it says paper here, but you're not looking at paper. So this is only true for positive charges. And in the world that you and I live in, almost every time that charges are in motion, in the electrical devices that we use on day-to-day basis, the electron is what's moving. So that's a negative charge. And so you could either flop over to a left-hand rule for negative charges, or I've come up with an alternative right-hand rule that works for negative charges, but that's kind of beside the point. But what you can see is if you have a wire that has charge moving through it, that there is a magnetic field that is generated around that wire. And furthermore, if you wrap that wire into a coil, then you have a magnetic field that is through the central axis of the coil. And then if you wrap multiple coils, that just causes a bunch of magnetic fields to add up. And so that's what is going on with the electromagnet. So one of the other things to think about is how do permanent magnets get their magnetic field associated with them. And so if you were to look this up, which you might have in this or a previous physics course, that you'll read that there are things called ferromagnetic materials that have iron in them, because iron is the Fe is the symbol, the atomic symbol for iron, and ferrous and all of those kinds of things describe iron. And I guess you'd need to know Latin to understand where that comes from, but I don't, so I won't go there. And what you would read about are things called magnetic domains, but they wouldn't get to the heart of what is it that is, what charge is actually moving. So if you think about a typical atom, an atom has charged particles in it. And if you think about the Bohr model of the atom, that you have a nucleus that has protons in it that are charged, and as if you explore how magnetic resonance imaging works, then you'll learn more about proton spin, because if I have a proton that rotates on its axis, it has a magnetic field associated with it, and that's where magnetic resonance imaging comes into play. But typically, that the magnetism associated with proton spin does not enter into the equation of what's going on with permanent magnets, that instead has to do with electron spin. And if you've had chemistry, you know that there are various quantum numbers associated with electrons, and the Pauli exclusion principle, talking about how you can't have two electrons with the same spin in the same state, blah, 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 blah. Go back to your chemistry if you want to learn more about that. But you can think of the electron in a Bohr model being kind of like the Earth, that the Earth rotates around the sun, or moves in a circular orbit around the sun while it spins on its own axis. So using the Bohr model, which the model falls apart if you push it too far, but for these purposes, you can think that the electron's motion around the nucleus would be an electron moving, so there would be a magnetic field associated with that. However, it doesn't have a nice circular orbit that would yield a uniform kind of magnetic field, but it is actually the spin of the electron that yields the magnetic field that is useful in describing what happens in a permanent magnet. And the thing about ferromagnetic materials and some of the other rare earth magnets is that they have an electron that ends up being unpaired, and so there is a net magnetic field, typically in one of the the valence electrons, one of the electrons in the outermost shells. And if you can get enough of them to line up the same way, you create these magnetic domains that can then be grouped together, usually in the presence of an external magnetic field, so that you get a net magnetic field in the material. So permanent magnets are made of materials that have unpaired electrons so that there's a net magnetic spin field, a net magnetic field associated with unpaired electrons that you can then expose to an external magnetic field and get a bunch of them to line up together, and then you take the external field away and they'll hang out lined up together for some period of time. So that's a permanent magnet. The other one that's of interest is potentially the Earth's magnetic field. And if you do some research, you learn about some kind of dynamo effect. But a simple model to think about is, that below the Earth's crust, that below that mantle part of it, that you have a liquid interior, which the people in some people in Hawaii are experiencing, with lava taking out their town. But that there is molten material in the innards of the Earth, and that molten material is hot enough that it has become charged, that there is a net electric charge to that material. And then if you know what convection is, that there are convective currents of this molten material within the Earth that present moving charges that create Earth's magnetic fields. Now, the Earth's magnetic field is very wimpy compared to what you can create in a permanent magnet, or the kinds of fields that you can create in an MRI machine are just, thousands and thousands of times stronger than the Earth's magnetic field. But the Earth's magnetic field is very important. The image that you see on the screen shows the sun and the Earth's magnetosphere, and the Earth's magnetic field ends up helping protect the Earth from lots of stuff that the sun blows off. Now, if you've done any research into electromagnetic pulses and solar flares, etc., you realize that our magnetosphere is not strong enough to protect us from everything, but it is enough to protect us from a lot of what normally happens on the sun. And it's also responsible for the northern and southern lights, the aurora borealis and the aurora australis, that charged particles blown off by the sun as part of what's oftentimes called the solar wind come to the Earth, and the Earth's magnetic field in essence traps them, and they kind of bounce back and forth between north and south pole of the Earth's magnetic field, and some of them leak through and end up ionizing some of the upper atmosphere, causing a plasma that glows all kinds of different pretty colors. One of the things that happens from time to time to the Earth is the Earth's magnetic field changes, and that is theorized to be a result of changes to the convective currents within the Earth. And that, so there are, what? There is evidence in some rocks, etc., that the Earth's magnetic field has swapped multiple times over the billions of years that the Earth has existed, if you buy that model. Um, and so, if the Earth's magnetic field flips, that there's a period of time during the flipping where there's not a coherent Earth magnetic field. And so we're not as protected from stuff coming at us from the sun. And so there are some theories out there that suggest that major extinction events can be linked to changes in the Earth's magnetic field. And if you're a pilot, you know that the Earth's magnetic field has been changing, and it's been changing to the point where they're having to start uh, having to relabel some landing strips, because landing strips are typically labeled based on magnetic compass reading. And if the Earth's magnetic field is shifting, which it has been for a bit, that you want to be able to keep the landing strips lined up with magnetic field readings. And so there have been a few, and maybe a lot, of airports that have actually relabeled some of their landing strips. So, anyways, the Earth's magnetic field is changing. It constantly changes, but we've been overdue for a major magnetic field change. And if a change were to happen while you and I are around, that might not necessarily be a good thing. But, anyways, back to the main mantra that the source of all magnetism is moving charge. So, in an electromagnet, it is electrons moving through wires typically that create that electromagnet. In permanent magnets, it's an atomic level process where you have unpaired electrons that have a net magnetic field that can then be ganged up with by other atoms in the presence of an external magnetic field, and then they stay hung out together with a net magnetic field. And then the Earth has molten stuff undergoing convective currents internally that can help describe where the Earth's magnetic field comes from. Bye bye now.